the bell icon on the YouTube app and never miss another update.
In earlier class with regard to this method, which is conjugate beam method, we had actually discussed how to analyze or how to determine or calculate slope and deflection of any beam with the help of the conjugate beam method. Primarily, this method has been seen much useful in such members which have what which have non-uniform flexure rigidity, right? In such cases, this method has proven to be very useful. Now, in previous class, we had discussed what is this method all about, and we had also solved a problem which was a simply supported beam with a point load at the mid span, and we calculated its what slope and its deflection. And there was actually two theorems or two statements behind it, which which had actually told us that the slope, if you have to calculate the slope of the real beam, because here you will be having two beams, one will be real beam and the another will be what, imaginary beam, which is also called as conjugate beam. Here, if you have to calculate the slope of any real beam, that is equal to the shear force at that particular point on the conjugate beam. Fine. And if you have to calculate the deflection at any point on the real beam, that will be equal to what? Bending moment at that very point on the conjugate beam. Fine. This was with regard to the simply supported, the case that we had earlier solved was simply supported beam with the point load at midspan. Now we'll try to find out other options as well, other methods parabolically, and its maximum bending moment will be how much at midspan? It will be simply how much? WL square by 8.
WL square by
How much? WL square by 8 at midspan. That means at center, WL by 2, WL by 2. Okay. Now, this was with regard to your bending moment diagram. Now, from the bending moment diagram, you have to actually formulate one more diagram, which is called as M by EI diagram, which is actually, this is your M by EI diagram, similar to the diagram which you have proposed for what? Bending moment diagram. This is called as M by EI diagram. And again, at the center, it will be how much now? M by, it will be M by, sorry, it will be
WL
your
square by 8 EI.
WL square by 8 EI. Fine, at this very point, which is at the center. And this is your point A, this is your point B, this is your and this will be your reaction VB. Now this is called as conjugate beam. This is your conjugate beam. Now this diagram, which was actually moment diagram, has now become what? A beam, a imaginary beam. It's an hypothetical beam, which is also called as conjugate beam. Now the loading of the beam, this conjugate beam, is as per the diagram bending moment diagram, it's your load. Area, this area is your now, this hole is your moment, it is your load now. Now, in order to calculate the total load, first of all, total load will be how much? Total load on conjugate beam. Total load on conjugate beam will be equal to 2 by 3 of how much is the span, it's L, and how much is the height at this very point, it is WL square by 80I. Fine, this is the total load on conjugate beam. This will be equal to WL square by
WL cube.
sorry, Q by 12 E.
Yeah.
Fine. This is what? This is actually the total load that is on the conjugate beam now. That is on the conjugate beam supports. That is VA and VB. Therefore, you can say your VA will be equal to, now that it is uniformly distributed over the both spans, VA will be simply half of the total load, right? How much will be that? WL cube by 12 EI. How much will be that? It will be simply WL cube by 24 EI. Right? It will be simply WL cube by 24 EI. Now, if you have to calculate VB now, your VB will be how much? It will be again similar to that of VA, that is WL cube by 24 EI. Okay. Now, as you have already understood with regard to the calculation of slope at A for real beam will be equal to,
Yeah.
it is equal to shear force at A for conjugate beam, right? It will be equal to shear force at conjugate beam. That is equal to how much? Therefore, your slope at A will be equal to shear force. How much is that? WL cube by 24 EI. Okay, now you have understood that you can simply calculate the slope at A when you have any conjugate beam, and you will calculate its shear force. Fine. Now comes the slope. Now, if you have to calculate, slope is already done. Now comes deflection. Now, as you already know, deflection will be maximum at which point? At center point, at midspan. That means deflection at C for real beam will be equal to bending moment at C for conjugate beam, for CB, that is conjugate beam. Therefore, you can see that First of all, we have to calculate what? Bending moment at point C. That will be simply equal to VA times how much? L by 2. VA times L by 2 minus load. How much will be that? 2 by 3 of L by 2 into WL square by 8EI multiplied by 3 by 8 of L by 2. Fine. This is your what? VA. If you are calculating moment at point this, if you are calculating moment at point this at C, therefore this is your reaction, that is VA multiplied by its distance, and then comes the load, which is how much? 2 by 3 of L by 2. This is your L by 2 multiplied by this height WL square by 8EI, and then centroid. Centroid will be stop talking. This is your how much? 3 by 8. That is the distance from the point from which you are calculating your what? Movement to the centroid. That comes out to be 3 by 8. Therefore, you know what is VA. How much is VA? It is WL cube by 24 EI multiplied by L by 2 minus, just solve this one and it will come out to be WL4 divided by 2 into 8 into 24 EI. Right? Therefore, solving it will give you how much? WL4 by 48 EI minus 3 times WL4 divided by 384 EI, that is equal to 5 times WL4 by 384 EI. This is your how much? This is your deflect bending moment at point C. This is your bending moment at point C. Now, in order to calculate the deflection, at C, deflection at C for real beam is equal to bending moment, which you have already calculated. How much is that? 5WL4 divided by 384 EI. Okay, this is your deflection at C for the real beam. If you want to cross check it from the previous methods by which you have calculated slopes and deflections, you can cross check that as well. This was with regard to this case. Now we will do a problem. In this problem, what we have a beam, we have a simply supported beam, which is having actually two types of flexure rigidity on the throughout the length of the beam, and it is supported with a point load at the center. Let's say that beam is like this. Draw this beam. it is simply supported this way. It is simply supported at this point. Let's say this is point A, this is point B, and this is your point C. It has a load W, and this is point C, and this is at a distance of L/2, and this again is at a distance of L/2. Okay, that means at midspan from A to C we have a flexure rigidity of, or modulus of elasticity as I, and from C to B we have a modulus of elasticity of 2I. Now what does this mean? E is a material property. We say that there is a variation in what? There is variation in flexure rigidity, and in flexure rigidity we have two things. One is modulus of elasticity, that is actually the property of the material. What properties are we using? Fine. And then is I is simply modulus of elasticity, and modulus of elasticity, it will include what? It will actually include the dimensions. Therefore from the diagram itself you can here say that on part A to C, we have modulus of elasticity, say 1. And from part C to B, we will be having modulus of elasticity as 2. That will actually depend upon what? Cross-sectional dimensions. That will depend upon B and D, cross-sectional dimensions. And on the basis of these cross-sectional dimensions, which are breadth and width, you will be having different modulus of elasticities, like the way it is here. Therefore you can simply say, while having a look at this beam, you can easily say that there is a variation in what? There is not any material variation. There is not any non-homogeneity of material, but there is a non-homogeneity of what? Modulus of elasticity, that is the cross-sectional dimensions. Here again, now firstly, you know, the first and foremost thing is that you have to draw its what? Bending moment diagram. You have to draw its bending moment diagram. A simple bending moment diagram, it will be a simple beam and a point load at center. It will give how much? It will simply give WL/4 at center, which is at a span of L/2, which is at a span of L/2. This is your point A, this is your point B. Okay, you have two different points, and then you have to actually calculate what? Draw its conjugate beam. You have to draw its what? Conjugate beam. Now on the conjugate beam you can simply say this is your now 1 by EI, this portion, and this is your 1 by 2I CI. 1 by 2I CI. This diagram can be, these both the diagrams can be different. This can be somewhat like this. It depends upon, oh sorry, now this diagram can be somewhat like this. Doesn't matter how is it, we are actually concerned with what? The values, which is M by EI. And at this very point, again we will be having WL/4, but EI is different for both the cases. It is different for both the cases. It will be different for this portion and it will be different for this very portion. That means we will name it by A, B and C. When we are actually checking here first of all, what we have to calculate? We have to simply calculate what is the total load on conjugate beam. That is what? That is simply M by EI diagram. It is M by EI diagram. And now we have thickness 1 by EI for which portion? For left portion. And we have thickness 1 by twice EI for your right portion. Okay. We have two thicknesses for two triangles. Now, if we will try to find out what actually happens with the left triangle or left load component. Sorry. Therefore, in order to calculate the total load first on the left portion, what will be your total load? Simple. It will be half of base. How much is that? L by 2 into WL by 4 multiplied by 1 by EI. That is the thickness portion. This will be equal to how much? It will be equal to WL square by 16 EI. Fine. This is the total load on left component, left compartment. Therefore, this was what? This was actually load. Now, if you have to calculate the moment, let's say we will, because ultimately we have to calculate the bending moment. Let's say we are calculating the moment about A. Now, how much will be the moment about A? Simple. Load, how much is load?
0.
Load is simply WL square. Sorry, it's square here. WL square by 16 EI. And if you have to calculate your moment about A, it will be simply how much? 2 by 3 of L by 2. Hai? It will be 2/3 of L by 2. Therefore, that will be equal to WL cube by 48 EI. This will be your movement about A. This will be your movement about A. Now, if you will see what happens to a right side component. Right side component, we have total load how much? Again, same, half of base, which is L by 2 into WL by 4, that is the height, multiplied by 1 by 2 times CI. Because I has changed now, I has changed from I to 2ISI. Therefore, your total flexure rigidity here becomes 1 by twice EI. So you can here say that the total load is now WL square by. Fine. Again, calculating the moment about A. Moment about A. That will be again equal to WL square by 32 EI multiplied by A to L by 2 plus 1 by 3 of L by 2. Right? 1 by 3 of L by 2 now. And you have to add the, because you are calculating movement about A. You are calculating movement about A. That is why you have to add the L by 2 portion. Therefore, your movement about A is equal to WL cube by 48 EI. Okay, this is the total movement about A with regard to the right side component, which is CB component. Now, as you already know that the total load now, how much will be the total load for compartment, left side compartment and right side compartment? That is equal to WL square by, how much was it? 16 EI, and another was, I guess, 32. WL square by 32 EI, which comes out to be 3 times WL square by 32 EI. Fine, this is the total load. Now, total movement about A, again, you have to add the both. Total movement about A is equal to WL cube by 48 EI plus WL cube by 48 EI, which comes out to be WL cube by 24 EI. This is the total load, sorry, total movement about A. Fine. Now, as we already know from the previous slides, we have, okay, now we have calculated what? Total load. This is your total load, which is already being calculated. And we have calculated total movement about A. This is your point A, for which we have divided into this figure into two compartments, wherein A, let's say this is point O, let's say this is point O, and we calculated the total load on AOC first, and then calculated the total load on COB second, and then added them up. And we also calculated the movement about AOC about A, and then we calculated the movement of the due to load about A. Fine. Now, what are we left with? We are left with, we had total load. This is our total load. We have our total movement, and we have individual movements also of to left side and right side. Now, in order to calculate, finally, we have to calculate what? Firstly, slope, and then deflection. In order to calculate our slopes, we will be having a maximum slopes at point A and B. That's a quite understandable thing. So therefore, we have to finally calculate what? We have to calculate the reaction. That is VA. We have to calculate reaction VA and VB. So in order to calculate now VA and VB, how can we calculate these reaction or these shear force? We simply will taking movement about A. Therefore, if you have to calculate the movement about A, it will be simply equal to VB times L is equal to how much? WL cube by 24 EI. Simple. WL cube by 24. VB times into L, if you are calculating movement about A, VB is what? VB is your this reaction times length multiplied by जो ऊपर से इसका total movement आ गया. Therefore, you can here calculate VB is equal to WL square by 24 EI. Okay. Now this VB is how much? What is this? What is VB? VB is simple. It is shear force. It is actually, what is it? It is basically, first of all, it is also shear force at B. On which beam? On conjugate beam.
Conjugate.
Fine. And now we know that this is equal to what? Slope at B on real beam.
On real beam.
On real beam. Fine, good. Now we have to calculate VA. How much will be VA? This won't be equal here. because we have different flexure rigidities, right? We cannot say here that slope at A is equal to slope at B. Reason being different flexure rigidities. So in order to calculate now slope at A, how can we calculate it? We have total load, it's here. It is how much? 3 times WL square by 32 EI minus how much? WL square VA. We have to subtract VA from the total load, that is 24 EI. Fine. That comes out to be 5 times WL square by 96 EI. This is your, again, this is what? This is your slope at A on conjugate beam, which is also equal to now. Here we have calculated what? We had calculated shear or reaction at point B, which was supposed to be the difference of total load, which is WL square by 32 EI minus what? VB. How much is that? That is WL square by 24 EI. Okay, and that comes out to be 5 WL square by 96 I. Now this is what? This is your one. This is the reaction at point A, and also it is equal to what? Shear force at A conjugate B. And it is also equal to slope at A on real beam. Now you are done with what? Slope at A and slope at B. Now you want what? Bending moment at point C on conjugate beam. Right? You want bending moment at point C on conjugate beam now. Now, in order to calculate your bending moment at point C, it will be simply equal to VA multiplied by L by 2 minus WL square by 16 EI times 1 by 3 of L by 2. Now you know this is your bending moment at point C on conjugate beam, which is VA, that is the reaction at A multiplied by L by 2 minus times WL square by 16 EI times the centroidal distance. Now VA is how much? 5 WL square by 96 EI multiplied by L by 2 minus WL square by 16 EI times L by 6. You solve it and your bending moment will come out to be WL cube by 64 EI. This is your what? This is your bending moment at C for real beam, which is also equal to slope at C for conjugate beam. Fine, which is equal to how much? WL cube by 64 EI. Therefore, you have calculated now what? Slope at point A for real beam, slope at point B for real beam, and you have calculated deflection at point C for real beam. Fine. You got slope at 2 points and you got slope at what? Midpoint. Because we are actually calculating the maximum values. Maximum values will be certainly for slope it will be at ends, and for deflection it will be at midspan. Okay. Now I guess you do one problem by your own, huh? Write down a problem. Okay, I'll write it down here. Do it at your place. Find the deflection of the beam shown in figure taking E is equal to 210 multiplied by 10 raised to the power of 6 kilonewton per meter square, and I is equal to I1 is equal to 160 into 10 raised to the power of minus 6 m raised to the power of 4 m raised to the power of 4, and then I2 as 120 into 10 raised to the power of minus 6 m4. It's a simple problem. Simply you have this beam which is having two loads and a point load 90 kilonewton, and this is your I1, this is your I2, and the distance is 2.7 meters from this point, and it is 1.8 meters this portion. Okay, point A, B, and C. You have to calculate the deflection of the beam as well as the slopes. Fine. Okay, I think here we will end the class. Chalo, then take care. Huh?